Hello, ENET 140 Op Amps class. This is Bellingham Technical College Winter 2020, and this is the second recorded lecture for our Fiore textbook chapter 4 on basic op amp circuits. So when we left off at the end of the last recording, we were doing non-inverting voltage amplifiers, and in that case our voltage signal was being applied to the non-inverting terminal, and we were looking at the effect of the feedback resistor network on voltage gain. So now we're going to switch gears a little bit and look at what happens when we apply a voltage signal to the inverting terminal. And as you're probably not surprised, we will show with Kirchhoff's voltage law and current law that we will get an inverted signal, negative if we're putting in a positive DC signal, or if we have an AC signal going in, we'll show that we get a voltage signal on the output that's 180 degrees out of phase. So here's our basic schematic for our inverting voltage amplifier. So we have our basic op amp. We have the non-inverting terminal grounded in this case. So we're going to apply our AC voltage signal that is coming up reference to ground. It's going to come in through the inverting terminal resistor into the inverting terminal. And then we have our feedback resistor connecting the inverting terminal to the output. And then our nice amplified signal flows out over our load resistor, and then we connect back to ground. Just as a note, one of the reasons that I like to write a lot of ground references rather than just showing maybe a floating reference, if I know that a signal is ultimately referenced to ground, or that an output is going to flow through some network to ground, I like to show that because I like to remind myself where my ultimate zero reference point is. Because we're going to be defining something called a virtual ground in this section, in fact right here, it's very important to know where the real earth ground is. So please feel free to use that little 3-bar earth ground symbol liberally when you're sure you're at ground, and that gives you a good 0 point to reference. So on those lines, we'll go ahead and KVL a little bit and apply our rules of idealized op amps to the circuit. So we'll start with our input signal. Again, we come up from earth ground, we have a signal. Because we have a voltage signal, we can get a current flow. So we'll have a current I in flowing in over R sub I. And it's going to come to this node that I have labeled V sub A. So current is not going to flow into the inverting terminal because we have infinite input impedance into our op amp. So all of V in is going to flow into this node here that it has a voltage of V sub A, and then it's going to flow through the feedback resistor to the output. So R sub I and R sub F are actually in series with each other. So that's pretty cool. We could define what different voltages are relative to one another if we knew what V sub A was. So that would be useful, and good thing for us, we have a second rule of idealized op amps that can give that to us. If we define the voltage at the non-inverting terminal as V sub B, we know that V sub B and V sub A are the same. Well, V sub B is at ground, is at earth ground. So if V sub B and V sub A are the same, and V sub B is at earth ground, V sub A is at effective ground. It's not a true earth ground because it does go through the op amp, but it is equal voltage to V sub B by a function of the op amp, the idealized op amp. So we call this a virtual ground, and it actually has a different symbol. So we can say that V sub A is at 0 volts or is at ground, and that allows us to say something about I in. We can define I in as V in minus earth ground. So if we have R sub I, we have I in. We know that I in doesn't really branch at this node because no current can flow into the inverting terminal. So all of I in, which we've now defined as Vn minus Va over R sub I is going to flow over R sub F. Now if we look at we ultimately want an expression for V out. And here's where we have to be a little careful of our signs, and it's one reason I like drawing the grounds. We can kind of do a KVL from this ground up through our input voltage source over our R sub I to this node. No current goes into the op amp. We know that this node is at 0. Then we can drop voltage because the positive current's going to continue to flow in this direction. We're going to drop voltage over R sub F to V out. And then we're going to drop more over the load resistor to ground. But if we're interested in the voltage at V out, we've dropped it below the level of our virtual ground. And it's that drop that ends up giving us the inversion. So it literally falls out of the math there when we write some expressions. So let's step through the math that goes with that. So we're going to say V sub A, which is here, is 0 volts. That's our virtual ground. So we can use Ohm's law to define IN as Vn minus 0, which is Va, divided by Rn. I amp, meaning I into the amplifier, is 0 because we have infinite input impedance. So IN is the same as I feedback, the current flowing here through the feedback resistor. Okay, cool. So now we're going to define a voltage drop over the feedback resistor. It's going to have a magnitude equal to V out minus VA, and it can also be expressed as RF times IF. Okay. Now let's get the sign straight. This voltage drop will have a magnitude, but it's a drop from here to here. So V out is going to be actually this voltage minus IF times RF to get to V out. So V out is VA, which is 0 volts, minus the current flowing through the feedback resistor. And so that's where you get the negative sign here. So V out is equal to negative RF times IF. So now we just do some algebraic substitution. IF was equal to IN, and IN is equal to Vn over Rn. Hey, we're getting pretty close to being able to define a gain here. So we've rewritten V out over here, negative Vf times IF. We substitute in IN equals Vn over Rn for IF, and we get V out equals negative R feedback over Rn times IN. If we want to define gain as a voltage ratio, all we do is divide both sides by Vn, and we get V out over Vn is negative value of the feedback resistor over value of the inverting input resistor. And again, this negative would indicate opposite sign for a DC signal versus what you put in, or 180 degrees out of phase versus the input signal for an AC signal coming in. Super simple. So things to remember, again, gain is being defined by values of the feedback resistor network only, and we have a negative sign here because we are flowing conventional current over a resistor and dropping resistance relative to a virtual ground. So it just falls out of our KVL. So if I want to do a little example here, we've got a 5 kilo ohm resistor for Ri and a 20 kilo ohm resistor for our feedback network. We're putting in a 100 millivolt signal. This is an AC signal, so I'm assuming that's probably an amplitude. We just define the gain as RF over Ri. There's a negative sign indicating that the voltage signal here is 180 degrees out of phase with our input. And so we get a gain of effectively -4 or 4 inverted. So if we put 100 millivolts amplitude in, we would get 400 millivolts amplitude out, 180 degrees out of phase. So that's something we could easily see on our oscilloscope. Okay, have another example here. Somebody tells us that we've got an amplifier with a 15 kilo ohm input impedance, and we have a gain of 10 inverting. So right here, inverting means we've got excuse me, our signal going into the inverting terminal. And we're presuming that this is a voltage amplifier. So we're going to have the same kind of general design that we had before, but how do we deal with this? We don't necessarily, we've got that virtual ground. So when we look at input impedance to the inverting amplifier, we'll scale right back to it. One thing we have to remember is this terminal, even though it has infinite input impedance into the amplifier and no direct path to true earth ground, it's a virtual ground. So it counts as a path to ground for the input. So if we're looking here from our input signal into the amplifier, which is the way we define input impedance, is we look at the path to ground from the entrance point to the amplifier circuit, which is here, and we're looking here, looking into the amplifier and saying, what's the resistance or complex resistance, impedance, between me and the nearest ground, the easiest path to ground? Well, here's a virtual ground right here. What's the resistance between the entry point here and this virtual ground? Well, it's just that resistor. So our R sub I effectively creates and defines the input impedance for this inverting voltage amplifier configuration. So very different than the non-inverting, where we actually had to add an extra resistor to ground because our voltage signal is going straight into the inverting terminal, no virtual ground. So that might help us say something about our design. Well, we know that the ratio of RF to RI equals 10. If we configure it in the inverting style, we will get an inverted signal. And we can use the fact that a 15 kilo ohm input impedance is desired to define R sub I. So R sub I becomes 15 kilo ohms. That defines the input impedance, the resistance between the input signal and that virtual ground at the inverting terminal. If we know R sub I is 15 kilo ohms and R sub F over R sub I is 10, R sub F is 150 kilo ohms. Easy peasy. We have both of the resistors for our feedback network. We've effectively designed our circuit. Okay, another example. You'll notice Fiore has quite a few examples in these first couple of chapters, and then he ramps it down with the more complicated designs like the Summers and the full-up differential amplifier. So we'll go through quite a few of these because there's a lot of variations. And in fact, the more complex variations you might take a look at and go, well, gosh, that's just an inverting or non-inverting, or you know, maybe it's a parallel input for a current signal input, but otherwise the same. So you'll see the same trends. So we'll look at another variation here. So we're given an amplifier with capacitors in parallel with the feedback resistor, and in parallel with the supply voltage, and a variable resistor on the output. Okay, so we've got supply capacitors of 0.1 microfarads each, and that's just to prevent an AC signal from affecting the supply, because we're putting a DC supply in. So we would, in this case, if we had, for any reason, we had some kind of AC signal coming into the supply, it would shunt to ground and then not come in and affect the amplifier. We want the supply voltage to say DC, so that's good. And we have a 2 picofarad capacitor in parallel with our feedback resistor. That's a pretty small capacitor, but you know, theoretically, if we had a high frequency input signal, it might be able to flow through that capacitor and bypass the feedback resistor. So the very fact that we have a capacitor there says that now our gain response is going to be a little bit frequency dependent, because remember, our gain is negative RF over RI, so the effective impedance of the path through the feedback would be less, a little bit less anyway, if you were high frequency, because more of you could flow through this capacitor with very little resisting you, very little effective impedance there. So otherwise, we've got our input signal, and that's referenced to ground. It's not shown. It's coming in through a 15 kilo ohm input resistor, R sub I. If you were a DC or a low frequency signal, you'd flow mostly through your 200 kilo ohm feedback resistor to this point here, and then your output over the load will be dependent on this pot. So you kind of have a double selection for your amplification. So if you're going to point VA, if you had like a 1 volt DC signal, say, coming in, you would end up with a signal at VA equal to negative 200 over 15, and then your output going out into your circuit would be dependent on how much of this 10K pot you were selecting. So this is just another nuance on the inverted amplifier, and just shows a little bit more selective version of your load resistor. Let's see if there's anything else super important. We can look at whether or not a 2 picofarad capacitor is likely to affect midband frequency. We now have a Z feedback because we have a complex impedance. We can use the 741 general purpose op amp as a gauge for midband frequency. So what we're doing is seeing how frequency dependent we're going to be with a 2 picofarad capacitor, because it's not a very big capacitor. So we know that our upper critical frequency with a 741 is about 500 hertz, which is not all that high. So we could take a look at the actual reactance for that capacitor and see how big it is. Is it really huge at this frequency? So we can go back to our AC fundamentals and look at our X sub C, which is the capacitive reactance, the effective resistance of the capacitor. So you got 2 pi times the frequency times the capacitance, so you got 2 times 10 to the minus 12. And this should all, in fact, there is an error, this should all be raised to the -1. Warning, this is -1. Capacitive reactance formula. So that ends up giving you 160 mega ohms. That's way bigger than RF. So the capacitor will act like an open for that, and we can pretty much neglect it. So for the frequencies that we're looking at, it's not really going to matter. And again, that's very likely because our upper critical for this particular op amp isn't a very, very high frequency. Had it been higher, that may have been different. So again, that'll depend on where your midband is in an absolute frequency standpoint versus the capacitive reactance here. So that's a good example of knowing, being able to design a circuit for frequency dependence and tune it by just simply using our formula. But we would of course have to use it correctly, the -1. This would have been correct had it been an inductor, and that had been in Henry's. Probably wouldn't have been using a big inductor with an op amp though. Otherwise, we can look at our, since we're going to neglect that capacitor, we'll assume that our entire midband signal will go through our 200K resistor, and we're back to 13 1/3 gain, unitless gain inverted, will get us to point A, and then we can decide how much of that's going to go over our pot and to the output, and the rest goes to ground. So that was a nice twist on frequency dependence, and something that we will see again, especially with lagging and leading, but very simple. Just taking a look at just the simple concept of capacitive impedance, and just remembering that like an inductor, is going to have its frequency dependence, and that's where pulling in the basic concept of our upper critical defining the midband. If we had had a lower critical, that would have been something else to look at. So just understanding benchmark frequency ranges that are important for an op-amp's operation. We can relate those with our real basic formulas to discrete circuit components that we might want to put in, and just use our rules from AC to see how it's going to react. React, pun intended. Okay, what if we have a current signal and we want to apply the same idea to get a voltage gain on the output? We can use the same thing. There's a parallel input and parallel output resistor feedback network that we can use that effectively accomplishes the same thing. This is called the inverting current to voltage transducer. It's called a transducer because we're converting one type of signal, a current-based signal, to a voltage-based signal. Otherwise the same. So same kind of configuration. We have the non-inverting terminal grounded. We define our node here at the inverting terminal. I like to call it V sub A. It's just easy to see. I have a current signal coming in. This time a current, it's labeled as voltage, but it will result in a current signal. We don't have a front end R sub I. All of the current flows through the feedback resistor to point V sub B on the output. Otherwise, everything the same. So our output signal is just simply going to be the inverse of our input signal times the feedback resistor. So if we have a device that produces a current as a signal, there's some instruments, for instance, that produce standard signals up to, say, 20 milliamps, probably using another op-amp themselves. And we want to evaluate that signal. That might be coming from the output of some kind of a photodetector, or the output of a strain gauge with a known voltage input. We're looking at change of resistance via current change. We might be looking at a changing current signal that's too small to measure or to read out. We're going to run it through this amplifier just to increase it so we can read it on a voltmeter, say. Our voltage output that we're going to read on a digital multimeter would be our input current signal times the feedback resistor, flipped with a negative. So bigger feedback resistor means we get a bigger voltage output. It's easier to read. So super simple. So you got an example here where you have a really tiny signal coming in, negative 50 microamps. That would be very, very hard to read with a digital multimeter. You hook up a standard op-amp in this inverting configuration and put a sizable feedback resistor over it. If you needed to have an output voltage of 4 volts, you would just divide 4 volts by 50 microamps, and you would know that you need an 80 kilo ohm feedback resistor between the voltage output and the inverting terminal. So a real handy way of amplifying a current signal, very simply. Okay, what if we don't want to change the sign? What if we have and we have a voltage signal coming in and we need a particular current? Maybe we're going to get a voltage signal out by flowing a current over a precision resistor, or for whatever reason we need to use an input signal to just drive a particular current flow over a load. In this case, the load is just a real resistor. We need a current signal and we need it amplified. We won't ask why. So we can use this configuration, the non-inverting voltage to current. So notice we've got the, when we think about series and parallel, let's back up a little bit. We talked about that in chapter 3. We had the series parallel and the parallel series, and we talked about how each one was particularly valuable for amplifying voltage or current. Look how we have current going to voltage, and so we have a parallel input in this case, and it's parallel because a signal coming in here has a choice. It can either go through the feedback network or it can go into the op-amp. And on the way out, same thing. You know, it's connected to the feedback network and the output. Over here, we have what would be considered a series. The input signal is coming into the op amp and it doesn't get a choice. There's no branch. This is not a parallel network. So our signal only has one place it can go, and our output only has one place it can go. So in a way, the load is connected in series to the feedback network. So this is a series combination. And so you can see it's used for voltage to current. And so there's a bit of a pattern there on input and output. So in any case, we have our voltage signal coming in. It's coming into the non-inverting terminal. Okay. And we have our V out, and it's connected in series to a load. And then to a node point, we've got an inverting terminal resistor, and it's R sub I because ultimately it's connected back up here and then down to ground. So we could relate the voltage at the output to ground, and we can relate the voltage on the input to ground because it's directly referenced to ground, and then we could get a gain expression, which is always great when you're amplifying, right? Well, this is pretty easy. We go from V out and we kind of run a test current through it. It's going to flow through the load to V sub A and is not going to flow up here because this has infinite input impedance, so there's no current through this branch. So I sub L must flow in its entirety from V sub A through R sub I to ground. So R sub I and R sub L, or the load resistor, are in series. So V out is just I sub L times R sub L plus R sub I. Not too bad. So how do we get a gain expression? If I just express V sub in without reference to I sub L, I can't cancel it out. Well, lucky for us, we can quick draw that property of op amps that the potential at this terminal and this terminal are the same. Whew! Good for us. So V in is the same as VA because this potential is the same as that potential for an idealized op amp with negative feedback. Great. That makes it easy. So I say V in is VA, and VA can be expressed in terms of I sub L as R sub I times I sub L. So V in is R sub I times I sub L, and V out is R sub L plus R sub I times V sub L. So I can cancel the I sub L's if I wanted an output voltage signal, which is great if that's what I wanted. If I just wanted an I sub L, which backing up here in my gain mania, I have to remember, wait a minute. Well, it's always great to calculate a V output. You might want to switch the load resistor. Here I got all excited and calculated verbally here a gain output, which is still valid. You often switch the load resistor. What we were going after was I sub L itself. So I can just take a look at this and walk through the math, and I'm going to want to express I sub L and V sub I in terms of one another. Remember, this is a voltage to current transducer. So I wanted the output current. This is a good example of how you can get too excited with the math. So I'll still retain my V sub A equals V sub in, and I will just play around with this expression. So I'll still use the series path, but I'm going to be going after this expression. And so what I'll want to do is substitute for V out, because I'm going to want to end up relating this to V in, which is what I know. So I go with this, and then I say V sub A over R sub I is I sub L, and just use this. Pretty simple. I can define that resistor in my circuit. I know what I have coming in, and now I know what I have flowing out in terms of current. Now, of course, if I knew what my load resistor was, then I could multiply by that and know what this circuit point was. But the idea of this whole thing was to get a controlled current. So I'm going to want to express the gain effectively in terms of a current. So instead of a gain, we get a current to voltage ratio. This is called a transconductance. It's 1 over the resistance, and it's known as a G sub M. So that's just that's a standard symbol, and it's called transconductance, or 1 over the resistance. You can think of it as the current to voltage ratio, output current to input voltage. But effectively, we calculate it the same way we did any other non-inverting. And of course, as I went through with my long-winded intro there, you could express the output voltage, which would be the drop over that load resistor, and the input resistor reference to ground. So if you were using that as a test point in the circuit, for instance, it would give you an indication of current. Or, of course, you could measure the current directly by putting an ammeter or current sensor in series with the load. So, transducer, voltage to current, amplified current, output current ratioed to input voltage is transconductance, G little m. So here's an example. Someone has a 4-volt signal, pretty big, and they want to know how much current is coming out if they have a 1 kilo ohm load resistor and a 20 kilo ohm inverting terminal resistor. So we can go through the formula we just derived and say, well, we know that this one doesn't really matter if we care about current. The current that will flow over that is going to be 1 over this resistor times our input voltage. So we end up with 0.2 milliamps flowing over that resistor. And this is a good place where our textbook author reminds us to check for clipping. And the rule is you cannot get a higher voltage flowing out of the output over whatever resistor network you have to ground. Total voltage between the output here and ground, then you can supply on the rails. So we know what the resistance path here is to ground. We know how much current is flowing out because we designed the op-amp feedback circuit for that. Now we have to make sure that a typical op-amp would have enough output voltage to supply that. So we know we have 21 kilo ohm resistor path to ground. We're going to try to flow 0.2 milliamps over it. That gives us a 4.2 volt drop between the output and ground, and that's way less than the 13.5 to 15 voltage supply limit that we would have. So we would not expect any kind of clipping, any kind of diminution of the signal due to the supply limits. So that's a good check. Another check is a typical 20 milliamp max output. And of course we're a couple of orders of magnitude below that, so we are safe both on the voltage clipping side and on the total current side. Okay, we have another more relevant kind of real-world example. We have a little instrument here that requires 100 microamps for a full-scale deflection. So this is like the galvanometers that were used in the old style voltmeters. So it's actually a magnetic device where you flow a certain amount of current through a little inductor coil, and it creates a little electromagnet that makes a needle deflect versus a set of permanent magnets. That's actually how ancient analog voltmeters worked. And some of those types of instruments are very, very accurate and are used for standardization today. So not to be dismissed. So in any case, this thing really needs 100 microamps for a full scale. So we need to design an op-amp that will allow us to have that much. And we need that 100 microamps to correspond to a 10 volt input voltage. So what value of inverting terminal resistor would we use to achieve that if we needed to? And in this case, you can really see the transducer characteristic of this device. We don't care what V out is here. We need a current for a particular application. So we are definitely going from voltage to current. So we need the transconductance, the 1 over Ri, that will give us that. So we basically go back to the formula we derived. We need the transconductance 1 over Ri being the right range. So we just plug right in. We have 10 volts divided by Ri. That better give us the right current. And notice Ohm's law units rule. So if you happen to forget the formula you just derived, you can almost do this on a units basis. So you just could multiply both sides by Ri and divide both sides by the current that you need. 10 volts divided by 100 microamps gives you 100 kiloohms. So that's what you need there to get this current output for that voltage input. You can also express that 1 over R sub I transconductance in Siemens, remember, because it's a 1 over ohms. So the transconductance, or G little m, for this circuit is 10 microsiemens. Okay, inverting current amplifier. So another flavor. So here this time we have a current source. So remember characteristics of ideal current sources. They will give you whatever current you need and will exact whatever voltage toll they need to give it to you. They have high, if not infinite, impedance. And the symbol of a circle with an eye and an arrow indicating the direction of conventional current. So we have some voltage rise from ground, whatever is necessary for our current source to give us whatever current we have. And that's defining an I in to this node. So we can see we have a parallel branch. So this is a parallel series configuration of feedback. Of course, despite the fact that it may be parallel, we know there's no current flowing through this branch because there's an infinite input impedance into that inverting terminal. There's an infinite impedance into the non-inverting terminal, but we're not trying to flow any current into it, so it's kind of beyond the pale. So we know all of I sub in flows through R sub I and down to node V sub B. So we could say that we could start defining V sub B and V sub A in terms of current flow. And that we know we've got our feedback resistor is now connected to ground. So we know the voltage at B is going to be whatever current is flowing through the feedback resistor and then ultimately up through the load to V out. So we can define a little network here. So we have I2 coming up through the feedback resistor, and of course it's being joined by I1 coming from the current source, like a little river convergence here. So we have a little Kirchhoff's current law node here. I1 in and I2 in means I1 plus I2 flows out through the load and back into the op amp. Because we have conventional current flowing back into the op amp, this is known as sinking. The op amp is sucking in current instead of spewing it out. So this is called a sinking arrangement. If conventional current were flowing out of the op amp, it would be called sourcing. So folks who are used to rivers, in karst areas, you have springs and sinks where the river comes out of the ground and disappears into the ground. So if the op amp were the ground and the current were the river, that would be an applicable kind of comparison. So we can define gain again for this circuit. Of course, or actually not gain, we'd be looking at looking for current. Yes, we will. Excuse me. So we will be looking for a current gain this time. Sorry. So we'll probably be interested in the current flowing over the load resistor, which will likely be I1 plus I2, which is I out. It's I over the load. Typically anything we're concerned with on the output is going over the load. So I1 plus I2 is going to be our effective output current. I1's or In is our input current. So we're going to want to define I1 plus I2 in terms of our feedback resistor network, because that's what we can define. Okay, so let's start walking through that. Okay, we have another virtual ground. Since we're at the inverting terminal here at VA, because the non-inverting is at ground and the inverting and the non-inverting have no potential difference, so V sub A is a virtual ground. It's at 0. We'll call In I1, I1 being defined as going through here, and I1 plus I2 we can call I load, because that'll be defined as the output. So we can do a little KVLing and define V sub B in terms of R sub I and the input current. So we can say V sub A is at 0. So 0 minus the voltage drop over R sub I, which is I1 times R sub I, is going to equal V sub B. So we have that here. And I1 is In. So we know V sub B. And V sub B is also equal to ground, real earth ground, minus I2 times RF. So we now have V sub B defined two ways that include In, Ri, and Rf, and I2. So if we set these two equal, because V sub B equals V sub B, so this term has to equal that term, we can apply some algebra and get an expression for I2 in terms of our input current, which we know, and a ratio of our feedback resistors. Well, this is great. All we have to do is add I1 and we have I load, because I1 plus I2 is I load, and I1 is In, and here's I2. So I1 plus I2 is In times Ri over Rf plus In. Maybe I'll factor an In out. Get rid of it. And then write my typical gain expression as I out, which is I load, divided by I in. We're going to have a negative sign because current is flowing backwards back into the amplifier. Again, this is called sinking behavior. And this ratio will end up just being this. So gain ends up being I load, which is this whole expression, which was this with the In factored out, divided by In. These two cancel. We keep the negative sign to indicate sinking, which would be a phase inversion in the current if we had an AC current. And so we can write a current gain expression for the inverting current amplifier as equaling -1 plus the ratio of the inverting terminal feedback resistor and the feedback resistor. Phase flip or sign change, 1 plus Ri over Rf. So a really quick example, we've got a 5 microamp current source. This is defined as positive 5 amps, so conventional current flowing this way. We have an R sub I of 33 kiloohms and an R sub F of 1 kiloohm. We don't care what this is unless we want to measure a voltage drop over it. So we can use what we just defined here for gain, if we were interested in gain, as -1 plus R sub I over R sub F, which is in this case just 33. So 1 plus 33 is 34. So the current flowing out of the op amp is -34 34 times whatever current is flowing out of this current source as our input. So it would just be 5 microamps times negative 34, which is equal to 170 microamps sinking, so flowing back into the op amp. And we can flip the information flow and do some design ideas with the same concept. Somebody says, well, hey, I have a standard op amp and it has a max current output of 20 milliamps, pretty typical, and plus or minus 15 volt supply, which means in reality we'll get about 13.5 on the positive and negative rails. And I need a current gain of 50 negative, so that means 50 sinking. Doesn't matter because the I out max of 20 milliamps would still apply whether it's sourcing or sinking direction. And I need to flow it over a 200 kilo ohm load. Okay, the current gain is basically, together with the maximum current output, is going to limit our maximum current input. And then the load resistor and whatever current output that we would have for a current input in this gain, we would use Ohm's law with our 200 kilo ohm resistor, load resistor, and make sure that that was less than the rail supply in either direction. So we're asked to find a circuit with feedback and op amp which will satisfy this. So basically it's a matter of just, keep everything within specs. So it looks like the first thing we want to do is we want to define the feedback resistor network. So we can go back through our current gain expression, -1 plus Ri over Rf equals -50. So that means the ratio of the inverting resistor to the feedback resistor is 49. Okay, we can go back to kind of our general rules of Ri and Rf being more than about a kilo ohm for general current limiting. This is a little bit less than our 10 kilo ohm to 100 kilo ohm range that we used for the non-inverting voltage amplifier, but generally we're working with semiconducting devices. Don't use resistors much below a kilo ohm. So then we want to think of, okay, what types of actual values of R sub I and R sub F? We know what the ratio is. We know we want to keep them above about a kilo ohm. So now we're going to pick some actual values that will keep I out and V out within their allowable limits. So we need I out less than 20 milliamps and we need V out less than 15 volts. Really it would be 13.5 versus ground. Okay, so we can assume that the 15 volts is going to be, or 13.5, will have to be greater than whatever the product of our load resistor and our actual current output is. Now in reality we will also, coming back to our circuit, we'll also have a voltage drop over the feedback resistor if you want to go all the way to ground. We're gonna make an estimation swag that this is pretty small compared to whatever our load resistor is. So we were told that load resistor is 200 kilo ohms. If we picked if we picked 1 kilo ohm for the feedback resistor and 49 kilo ohms for the inverting terminal resistor, we'd satisfy this ratio no problem. We'd have a reasonable size feedback resistor, and the voltage drop over it for any current flow, especially I2, which is less than I load, because I2 and IN equals I load. This term's probably going to be way small compared to this one. So we can just say, as a first estimate at least say, well, our I load, our I out, times our load resistor is going to have to be below the real rail supply, which I have 15 here. You could say it's 13.5. So you can say going down through here. Sorry, losing this a little bit. So your V out versus ground, again, is R load times I load. So I load is going to have to be less than rail voltage divided by your load resistor, which, if we had the full 15 volts, would be 75 microamps. So this will be less if we assume clipping at 13.5 versus in the 15 volt supply. So this, we would need at this point, if we were going to define anything further, what we're saying here is that your actual output current would have to be less than, in this case, 75 microamps, less if we're going to assume clipping at 13.5. If you wanted to know what input current that you could use, you would go back through your gain expression, and that would limit that. So we've pretty much come as far as we can with an op-amp design in this case, just by defining your current limit that you can use. And in that case, that is, admittedly, this question is not totally circuit design, because the circuit design really ended when we did the RF RI ratio and we picked an RF of 1 kilo ohm. Going through the exercise of an allowable voltage drop versus ground for V out and confirmation with I out max really had a lot to do with using our current gain and then saying, for this gain, what kind of input signal would we allow such that our output signal stayed below here in order to respect our rail voltage clipping limit. So a little bit of a real op-amp characteristic consideration there. So we're going to stop for this lecture before we get into a little bit more complicated op-amps. We're going to have summing, inverting, and summing non-inverting, and differential, and that will get us within spitting distance of the end of chapter 4. So we will resume with that, and thank you for listening.